Welcome to another fun episode of Schmidt-Kim. We're looking at AP topic 5.3 or unit 5.3, concentration changes over time. And our learning objective is to pay attention to this verb, identify the rate law expression of a chemical reaction using data that show how the concentration of reaction species change over time. So when we look at this one, all we have to do is identify. That's actually a very low level on Bloom's taxonomy. It's a very low level order of learning. We don't need to do much here. We just have to identify. And so how are we going to identify this stuff? Using data that show how the concentration of reactions species change over time. And that looks like graphs. And so if we look at our essential knowledge, it says the order of reaction can be inferred from a graph of concentration of reactant versus time. If we have a graph of concentration versus time, and then we have a linear plot that's negative, we're going to be able to identify that is a zero order. We're going to go over this in our lesson too, but I could teach it right from here. If a reaction is first order with respect to a reactant being monitored, the plot of the natural log of the concentration as a function of time will be linear. So when we have a graph of the natural log of the concentration versus time and it's a negative linear plot, we can identify that as being a first order reaction. And then if we look at a second order with respect to the reactant being monitored, a plot of the reciprocal of the concentration of that reactant versus time will be linear. And it's actually going to have a positive slope, but the reciprocal of the concentration versus time, a linear plot, that is how we are going to identify a second order reaction. All right, and then we look at, and of course you should be looking at your resource sheet. On your resource sheet, we have these wonderful equations that we look here, and what we call these are the integrated rate laws. And these help us to integrate the element of time. So if we know a certain change in concentration from time zero to a certain time, we can see how much time did that take. Or if we know the initial concentration and we know the time and we know the rate constant, then we can determine what the concentration would be at a certain time. So this is a very useful equation, or they are useful equations. Now, each order has its own equation. And so you can see on your resource sheet, there's those three listed there. Think of those in being the order, zero, first, and second, and then you will know how to apply those. So look on your resource sheet, know that the top one is zero order, the middle one is first order, and the bottom one is second order. Now, it is very useful to rearrange these equations into slope-intercept form. And you can easily rearrange these into slope-intercept form by simply adding the y-intercept of this. And what we end up with is all of these equations in slope-intercept form, in which we can see what value should be on the y-axis. For instance, on a zero-order plot, we should see that concentration is on the y-axis. And when we look here, we see concentration is on the y-axis. Wow, it's that easy. And then we look at a first order, we see the natural log of concentration should be on the y-axis. And what do we see? The natural log of the concentration on the y-axis. And then for second order, we see the reciprocal of the concentration is on the y-axis, and sure enough, there it is. All right, and so those are all really easy things to look at. Things that they mention here is that the slopes of the concentrations versus time data for the zero, first, and second order reactions can be used to determine the rate constant. And what is the rate constant? That is K. All right, a rate proportionality constant. A rate proportionality constant, if we look at y equals mx plus b, we see the m is the value of what? K. And so we can get the value of K right from the slope of the line, knowing that, it doesn't say it here, knowing that the value of K is always going to be positive. And then the last thing that we're going to look at is half-life, is a critical perimeter for, listen to this. This is the most interesting thing. Half-life is a critical perimeter for first-order reactions. For first-order reactions, they're telling us these are the rules of the game. We're playing AP chemistry. We're talking about half-lives. There is a half-life for 0, first, and second order, but 2 of those are omitted. Only one of those is integrated into our wonderful AP standards, and that is first order. So when we're looking at half-lives, we're going to only be looking at first order half-lives. So half-life is a critical parameter for first order reactions because the half-life is constant and related to the rate constant for a reaction by the equation. And so here's our equation for half-life. This is also on your resource sheet. And what you're going to notice is this doesn't have concentration involved in that equation. And so what does that mean? It means the half-life is independent of concentration. So as long as the value of K does not change, neither does the half-life. And we're going to go over that. But a half-life, we're looking at going from 1 molar to 0.5 molar, 10 seconds, from 0.5 molar to 0.25 molar, 10 seconds, from 0.25 molar to a half of that value, 0.125. It's 10 seconds. The time that each half-life or each successive half-life is exactly the same amount of time. And so I basically taught everything right now, but let's go to the lesson. All right, so here we go. So the purpose of the rate law. So integrated rate laws, the method of graphical analysis. So this allows us to a model for how the concentration of a reactant changes over time. To determine the order of the reaction, whether it's 0, first, or second order, we rely on graphical analysis. Now, only the plot corresponding to the correct integrated rate law will yield, this is very big, a linear relationship. So we're looking for those graphs. If it's 0 order, we're looking for it to be concentration on the y-axis. If it's first order, we're looking for it to be the natural log of the concentration. If it's second order, we're looking for it to be the reciprocal of the concentration. And then we're going to have all 3 of those graphs available to us. Which one are we looking for? We're looking for the one that gives us a linear relationship. And the graph that gives us a linear relationship tells us the order. Or let me say it another way. The graph that gives us the linear relationship helps us to identify the correct order, which is our goal for today. So there we go. So each integrated rate law can be aligned with the slope-intercept form. We already talked about that, y equals mx plus b, where y is a function of the concentration plotted on the vertical axis. M is the slope. We talked about the value of m being k, and we can determine the slope of we can determine the value of the rate proportionality constant as being the positive value of the slope. And then we have x is the time and b is the y-intercept. And if we look at this, I do want you to pay attention to this. Is a very big deal. The rate constant is, or k, is always a positive value. When is the rate constant a positive value? Always. Should you ever report the value of k as being negative? No. Are you going to see a negative slope on a 0 order? Yes. The slope is negative, k is positive. If we look here, we see k is equal to the negative m. M is negative. Negative times negative gives you a positive k. Or you can look at it this way. K is the absolute value of the slope. Do you see that? But you're going to get a positive value for k. All right, and we can see first order also has a negative slope and second order has a positive slope according to our integrated rate law expressed in the slope-intercept form. All right, so let's make this easy. And I didn't say the name, but also just one shout out to my one subscriber. He has 3 accounts. You know who you are, and I'm pretty sure you gave me all 3 likes on the last video. So thank you very much. I appreciate that. Keep up the good work. All right, so we're looking at the 0 order kinetics, 0 order kinetics. So again, if we're looking at 0 order, what are we looking for on the y-axis? Concentration. It should just be a graph of concentration versus time. So look at this. This is telling us what we need to do. we need to identify. How do we identify a first order? The plot of concentration versus time. If the reaction is 0th order, this plot will be what? Linear. All right, so what we're looking for is a graph that has concentration versus time and is linear. Do you see that? As a negative linear slope. That is telling us that is a 0 order reaction. 100% of the time, that will be a 0 order reaction. And so we have to make sure we understand that. And then we want to know the value of K. The value of K is the slope, except for is the absolute value of the slope, because K is what? Always positive. K is always positive. So we need to make sure we understand that. And so that's just how we identify. We look at the graph. If we see a graph of concentration versus time, it gives us a linear plot that has a negative slope. Then we know that that is 0 order without a doubt. All right. Well, all we're doing is identifying, so this is not super difficult. We go to first order kinetics, and we're going to spend a little time on first order kinetics because we talked about first order. We have to know something about half-lives along with first order. So we're gonna stop in the middle of this one and talk about half-lives real quick. But first order kinetics. A reaction is first order if the rate is directly proportional to the reaction concentration. We talked about that. In the integrated rate law, what should we see on the y-axis? The natural log of the concentration. How do we identify this? Identify is the plot of the natural logarithm of the concentration versus time. And if that's the case, it will be what? Linear. If it's first order, that's going to be a linear plot. What does that look like? Look, this is so easy to identify. You see a graph that has natural log of concentration versus time, and it's linear. What does that tell you? It tells you it's first order. That's exactly what it tells you. All you have to do is identify. All right? It's by definition. All right? And so make sure we pay attention to those things. All right. Now, there's another graph associated with first order that we need to be familiar with, and that is going to be one of concentration versus time. So if we look at this, first of all, I want to talk about a half-life, and then we'll talk about why this graph of concentration versus time, why do we need to know that about first order, and we'll talk about that. So the half-life, if we're looking at a half-life, it's very important to recognize when we talk about half-life that we're talking about it is the time, all right? It is the time. So the half-life is always going to be expressed as a unit of time. So the half-life is the time. It is the time required for a reactant's concentration to decrease to half its current value. To decrease to half its current value. So how long or how much time does it take for the concentration to go from its original value to half of its value? Do you see that? That's what we're interested in. But half-life is going to be expressed as a value of time, whether that is seconds, minutes, or hours. All right. One thing we should know about first order reactions is that they have a constant half-life, meaning their half-life does not change. Now, we don't have to go into 0 order half-lives or second order half-lives and look at their half-life equations or know their half-life equations or understand the relationship as far as the change in half-lives. Do they get longer or shorter? What we do need to know is that first orders remain constant, that the half-life never changes for a first order. And that's because a first order half-life is independent of concentration. If we go back to our equation, we look at this equation and we do not see anywhere in here concentration. So there's no value for concentration, meaning that the half-life does not depend on the concentration. And so even though the concentrations decrease over time, the half-life does not. All right, so let's take a look what a half-life means as far as this graph. Now, this is a graph of concentration versus time. One thing we should note is that we probably need to know something about graphs of concentration versus time. If that yielded a linear plot, what would we know? What would we know about it? It would be 0 order. So what do we know about this? It's not zero order. That's one thing we know. It's not zero order. But we don't know whether it's first or second order. But one thing we do know is that first order reactions, their half-lives are constant. That means they don't change. So from this graph, we can actually determine that part. And so we look at this, and we can see the original concentration is 1. Do we see that? 1. What's half of 1? 0.5. So we go to 0.5, and then we go to, we're going to from 0.5 to the line, and we see that it took 100 seconds. You see that? So the first half-life is 100 seconds. So if this is first order, that means the second half-life is also going to be 100 seconds. Now we just have to figure out what is that second half-life. So we are now at 0.5. What's half of 0.5? 0.25. So we go to 0.25, and then we go to the line. Zip. All right, and there that is. And what do we see? That's at 200 seconds. Now, how much time passed between the first half-life and the second half-life? So we would say, okay, here is time 2, here is time 1, and we would say it is what? 100 seconds. So do we see that the second half-life is 100 seconds, just like the first half-life is 100 seconds? By definition, because these two half-lives are the same amount of time, or they're the same half-life, we can say that this is first order reaction. All right, and so even though this is not a graph of the natural log of concentration versus time, we can use that the definition of a first order half-life to identify this as being a first order reaction. You see what I said there? We can use this to what? Identify, because that's our task today. So we're trying to identify. All right, so how do you anyway? Graphical determination of the order. You can determine if the reaction is first order by examining simple concentration versus time plot. If the time it takes for the concentration to drop to half its value is in successive half-lives is the same, the reaction is first order. That's what we just said. All right, that's what we just said. And so we can see from the equation again that the half-life is independent of concentration. There is no need to express concentration in determining the half-life, even from using the equation. All right, back to business. We're going to go on to second order kinetics. And on second order kinetics, here is our integrated rate law for a second order reaction and what should be expressed on the y-axis. Not just concentration, but the reciprocal of the concentration. And then what do we notice about the slope here? It's positive. We see it's a positive K. Now, K is always positive, but the slope is not always positive. And remember, in a zero order and a first order, the slope is negative. But in a second order, the slope is actually positive. And so we need to make sure we understand that. All right, so what is this going to look like? How are we going to identify a second order? Second order, we're looking at a graph of the reciprocal of the concentration versus time. And we notice that it's a linear plot. And it has a positive slope. So we can easily identify that as being a second order reaction. All right. Are y'all ready to put this to the test? You ready to put this to this test? This is going to be where it gets a little bit difficult. So I'm going to tell you it could take you as long as 5 seconds to be able to answer this very difficult question. It could take you as long as 5 seconds. If it takes you 6, it just means you needed an extra second. All right. So I'm not going to interpret that another way. So here is our data. The data below was used to determine the order of the reaction. I want you to determine the order of reaction, explain how you determine the order. So here we go. Here we go. Here's the graph. We're going to go through this real quick. What do we know from this graph? It's not zero order. What do we know from this graph? What do you mean it's not zero order? What's on this graph? How do we know this is not zero order? Concentration versus time is not linear. That's not zero. What is this? What is this a graph of? No, it's not the graph of concentration versus time. It's the graph of what? The natural log of the concentration versus time. So what do we know about this one? It's not first order. How do we know it's not first order? Because it's not linear. Now watch this. What do we know about this one? It is a graph of the reciprocal of the concentration versus time, giving us a linear positive slope. What does this tell us? It is second order. So this should take you seconds. If I put all three of these together just like that, and in under a second, you should be able to be like, oh, that's the graph. What does it say? Oh, it says the reciprocal of the concentration versus time. And why was my eye leaning towards this one? What's the one thing that's making my eye say this one? Because it's linear. It's the only linear plot. Does that make sense? Now, you do need to know the slopes because on your AP exam, they like to put the wrong slopes. They may put a linear slope and make it negative for this second order plot. Is that going to be the correct graph? No. What do you know about the slope of a second order? It's positive, and that's part of your identification process. All right, watch this one. This one we're not gonna itemize it. It's just gonna show it. Actually, we probably should itemize this one. This is a little harder to tell. But which one do you think this is? Top, middle, bottom. You think the middle? Let's take a look. Does that look linear? Maybe, I don't know. Does it look linear now? No. So I don't think that is what? What would this graph be trying to tell me? What information can I get from this graph? I can know that it's not zero order. All right? I can know that it's not zero order. I could also, from this graph, determine whether it's first order by looking at the half-lives. Of course, I don't have enough data on here to do that. But on this one, we see that there's a natural log of the concentration versus time. We see that it is a linear plot with a negative slope. Clearly, this is what? First order. So once you identify that being first order, now you should be able to write a rate law for this. Rate equals Ka to the 1, whatever the substance is, and then make sure you write that. And then what about this one? Is that linear? No, it has a little bit of a bend to it. It's not real easy to see, but once you compare it to this one, you can see that. On your test, you'll be able to, they'll make it very, very obvious to you what those are. All right, let's go over a couple of these real quick. I want you to look at these graphs and which of these graphs of concentration versus time is first order. Explain how you know. Explain how you know. So we look at this one and we see that this graph, and let's just go ahead and call this value 5.5. All right, what would be the value? What would be the concentration at half of 5.5? By the way, nearly every class has got this wrong. Say what? 2.75. Very good. This class is the real AP class. So y'all heard that. All right. So 2.75. All right. And so what we want to know then, well, how much time passed to get there? And what would you say that time was? Let's say 45 seconds. So 45 seconds. The first half-life is 45 seconds. Now, what do we know? If this is going to be first order, what do we know about the second half-life? It has to be 45 seconds as well. So let's see if that's true. So we're at 2.75. What do we need to go to? Nobody's grabbing their calculator. I hope y'all can still like this video, but nobody's grabbing their calculator. 1.375. You know what that looks like? It looks like this value right here. So what we notice then is what is the time between 120 minus 45 seconds. What do we notice about that? It's bigger than 45. We don't even need to know the answer. We know, hey, that's bigger than 45. What does that mean about this graph? Not first order. Do we see that? How do we know that? Because the successive half-lives are not the same. You see that? This is about identifying. See, we didn't have to identify what that was. We had to identify what it wasn't, right? It is not first order. All right. Now, what else is it not? Say what? It's not linear. Okay, that's true. But what else? What other order is it not? It is not zero order. Because if it were zero order, what would the plot be? It would be linear, and it's not linear. So it's not first, and it's not zero. So we're hoping that maybe it's the second order. We don't know. But if we had a menu of only options of zero, first, and second, well, we would say that was second order. Now let's look at this one. This is interesting. They don't even give us concentrations. They give us pressure. But if we have the partial pressure of a reactant, that partial pressure decreases over time because the number of moles of that gas in that container decreases over time. So we can use this partial pressure. And we start off with a value of 150. Agreed? 150. Nothing's working. All right. 150. There you go, that big dot. 150. And what we see is we want to go to what value? 150. 75. That's good. And so there's the 75. And then how long did that take to get there? Oh, that's not right. I went to the wrong line. Sorry. 75, somewhere right there. And we go to this line, and it is 15,000 seconds. So the first half-life is 15,000 seconds. If this is first order, how long will the second half-life be? 15,000 seconds. So we're at 75. What's half of 75? 37.5. Let's say that that's that value right there. So there we go. Now 30,000 minus 15,000. That's 15,000 seconds. And this was 15,000 seconds. The successive half-lives are the same. What does that mean? First order. And now we were able to identify that. Isn't that nice? All right. So let's see where else we can go with this. And you know what? You're going to have to get that in the next video because I'm needing some more views and I need those likes and subscribes. Let me hear that sound. What kind of sound does it make? A thumbs up sound. Those likes. Get those notifications. Ring the bells. All of those things. It's going to be fantastic. But for now, I got to go. Thank you for watching another fun episode of Schmidt Chem on Unit 5.3, the Integrated Rate Law.